Good afternoon, everybody. Going into our energy landscape for the United States, I want to first highlight what the projected or what the current US energy demands look like, as well as what people estimate that demand is going to be decades out into the future. So we have two graphs here on this page. The one on the left is the energy or electricity demand for the United States over various decades going back to 1990, projected all the way out to 2050. We have a similar timeline on the right graph, but in this instance, we're looking at the peak demand in those instances. So both of these are expected to significantly increase over at a rate greater than what we've seen in the past few decades. You can see in the 90s into the early 2000s and into the 2010s, we see a ramp up from 3,000 terawatt hours up to 4,000 terawatt hours of energy demand. But we expect to be up to close to over 7,000 terawatt hours as we go from now into 2050. That results in essentially nearly a double the demand that we currently have for all energy consumers. So that includes data centers, people's home heating and cooling, industrial and commercial applications, electric vehicles. This demand, both from a general demand and its peak, is only expected to go up. And so solutions are necessary for both the generation and transmission of this power to be able to meet those demands that we foresee. And so that brings us into a little bit of a more granular look and additionally a projection into the next 10 years of how we expect the distribution of where this power is being generated to come from. So over here on the left, our chart is representing the total capacity of each different type of energy generated. So we've got battery storage, we have solar, wind, hydro, nuclear, coal, and gas. And then the graph on the right is showing us of each of those segments what percentage of the overall total energy demand is provided by those specific sources. So a couple of trends that we can observe here is that into the back half of this decade and into 2030, projections expect that a significant increase in battery storage capacity and solar capacity to go up. We also are seeing a slight increase in wind capacity as we fight the overall demand that's going to continue to grow. As we look at how much percent each source contributes, we're noticing that there is a slight down reduction in natural gas and coal in favor of these renewable sources, that being battery storage, solar, wind, hydro, etc. And they become a larger percentage of the overall capacity that the US consumes. For the topics of our discussion today, we're going to focus a little bit closer into wind generation. Now, while it doesn't certainly have as large of a projected growth as battery storage and solar, that doesn't mean that it's going to go away. And it certainly has benefits to be considered. And there are certainly many simulation approaches that are worthwhile to discuss inside this domain. So here's just a quick overview on wind energy and how we're able to capture the power from the wind. And so the first question that we might ask ourselves is why wind energy? Why is that a potential solution for our energy demands, or at least a contributor to provide our energy? One benefit is that it's renewable, meaning that it does not have a recurring fuel cost. Once it's been installed, it's intended to stay there for anywhere from 20 to 30 years. They're highly scalable, which is quite beneficial because there are maps of the United States that you can look at that show what the average wind speeds are. And it's not uniform across the United States. There are certain areas where wind is blowing at a faster speed than others. So where you go where the wind is when you're thinking about deploying wind farms. And in doing so, the scalability is very important. It's not very common that you'll see a singular wind turbine out when you're driving along the highway. There's oftentimes multiple of them. To take advantage of that location where wind is consistent and at a velocity that we can generate power, and that there's the available room to scale that out to maximize and take advantage of that. It has the largest renewable capacity behind solar, and when we start thinking about offshore deployments, offshore meaning wind turbines installed out in the ocean, the deployment and land considerations really open up the doors there for scalability. Another benefit of offshore deployment is that you have the ability to take advantage of a oftentimes higher wind speed out inside of the ocean as well. And why do we care about wind speed? Wind speed, as we'll show here in a moment, is the most critical aspect of how to capture power, or how much power can be captured out of a wind turbine. And the way that that is computed is with the following equation. So P, the power in the wind, is 1/2 rho, which is the air density, times the swept area. You could think of that as the area of the circle created by the turbine blades, times the cube of the velocity of the wind. The velocity of the wind being a cubed term means that a double in the speed of the wind results in an 8x increase in the wind power. So on average, on land, in general, you could expect around 3 meters per second of average wind speed. Offshore, that average jumps up to around 6 or 7 meters per second. So that's just, again, the faster that we can capture that wind, the more power that we could theoretically generate out of the wind turbine. But it's not as simple as just saying, say I'm a wind farm planning operator and I'm trying to determine how many wind turbines to generate for my system. It's not as simple as just multiplying, the result of this equation by the number of wind turbines and getting the output. There are a few things to consider that result in only a specific proportion of that theoretical power actually being converted into energy. And so that brings us to something that's called the Betz limit. And what this is that wind cannot be 100% extracted. So that the result of that power equation, 100% of that power cannot be extracted, because what that would mean is that all of the power in the wind, all of its kinetic energy from the velocity and mass of that wind flowing through those wind turbine would result in no airflow after the turbine. All of it would be captured inside of it. And fundamentally, that's going to prevent any additional wind to come prevailing through and maintain rotation of the turbine. So a German physicist, Albert Betz, identified that by spinning an ideal propeller, up to 59.3% of the energy could actually be captured from the wind. Over here on the right, we have a graph of some different rotors and some different propellers and turbine designs, and what their theoretical coefficient of performance, C sub P, is. So typically we see in wind turbines a C sub P, or coefficient of performance, that's around 30 to 40%, meaning we're getting about 30 to 40% of the power that we calculated in the previous equation. When it comes to designing wind turbines, increasing that coefficient of performance as close to that Betz limit as possible is the fundamental goal to design an efficient system. Where that can be improved upon comes down to things like the aerodynamics of the rotor blades, maximizing lift to generate rotational speed, generator efficiency, making sure that we're not losing excessive losses as the power is being generated from rotational energy at the shaft of the turbine into electrical energy from the generator, as well as in power conversion. So connecting turbines to the grid requires power conversion, and any losses that occur across the entire process will stack up upon each other, from the rotational losses of friction in the bearings all the way to losses in the transformer in the power electronics circuitry. So when it comes to leveraging simulation, that is where we are trying to drive it. So why do we use simulation with Ansys? So Ansys is a physics-based simulation tool for all sorts of different engineering physics domains, including fluids, structures, electromagnetics, and optics. It's used to support design processes and reduce time to market and increase product performance so that you have a successful design moving forward. And it allows you to understand and address cause and effect relationships throughout the design process. So making a large decision is helpful when you have data to back up that decision. And simulation can help provide those data sets to make those educated decisions. And the implementation is important to maximize the ROI while achieving your product goals. We'll talk a little bit more about implementation, but specifically understanding when it makes sense to leverage simulation, when it makes sense not to, and really help come to that determination of where that can maximize your success without limiting or hindering your design and development process. So in terms of the wind turbine example, the case for simulation, there are numerous different areas, if you look at a wind turbine, where simulation can be helpful and leveraged. Everything from blade aerodynamics and turbine noise, so understanding and optimizing how the airflow flows over the blades, how the pitch of those blades impacts rotational speed. Because a fun little fact, these turbines are often designed to operate at a desired rotational speed. So if the wind is blowing fast enough to where that speed is going to be exceeded or is under that speed, the blades can be adjusted on their pitch to speed up or slow down the turbine to get it to a desired operating speed. Understanding how the noise impacts the nearby environment is also certainly a concern. These things are just installed for 30 years. So everything from a reliability perspective needs to be looked at from a high degree of scrutiny. Everything from blade structural forces to the deposition and wear out of the materials on blade composites and other surface coatings, repetitive forces and vibrations on the nacelle or housing. And then into actual power generation, making sure that we're converting as much of that mechanical energy that the turbine is creating into usable electrical power in the grid. And that can come down to optimizing and developing generators that can run at multiple speeds and are very efficient over operating ranges, and the associated power electronics to take that variable speed out of the equation so that we don't have any pushback or negative interactions with the greater grid that the wind turbines connect to. So here is what we kind of think of as an ideal simulation workflow. So it starts with a proof of concept that oftentimes results in what's the minimum viable product to get you the answer that you're trying to see, and determine what are the primary driving factors in that outcome. What are the main levers that you can change, and what are their results when you change them, and what are those impacts to the design objective that you're trying to meet. Once you have that proof of concept, you like that idea, then we move into a refined design standards and qualifications. So this is the refinement of the model, making different changes and understanding how that impacts the overall response. Try out different worst case scenarios that you expect your product to be encountering, and build up around the overall requirements that you've specified with simulation. Once you're meeting requirements, then it goes into the optimize and fine-tune phase. So this is, how can we reduce weight? How can we reduce cost by less material as well? Are there any other additional performance impacts that we can squeeze out of this system, or have we reached kind of the fundamental limit that we feel comfortable moving forward in? And all of that kind of falls under the product conceptualization and design umbrella. So those are kind of the three main steps that we typically suggest and see customers leverage when using simulation. Once the product is created, sometimes problems come up. So simulation can be used to help identify root causes of issues. Maybe that was something that was overlooked, or maybe you're at that point where the product conceptualization design phase occurred without any simulation guidance, and you're trying to deal with the problem now currently. Simulation can help understand and root out where those problems are occurring. And then long-term research and product development. So you have a product that's already out in the market, it's going fine, but you always want to consider thinking into the horizon. What's the next best thing? What's the next product that we want to add to this product family? So simulation can also help you understand where you can take that product and what might be worthwhile to investigate from an R&D or cost reduction perspective. Depending on where you start to consider simulation, like I mentioned, you might find yourself at a certain step inside of this process, and that's okay. This also could be potentially perceived as a hindrance to an existing design process that you have internally at your organization. You might be looking at all of this and say, that's a lot of simulations to run. We don't have a lot of time to add into our design cycle to accommodate these things. And frankly, the intention of simulation is to reduce design cycles and reduce risk. So we oftentimes consider looking at a more value-based simulation approach, where we really kind of boil it down and put the best practice workflow. You could do simulation and all these different steps aside for a moment and just ask yourself the simple question: what is the problem that I'm facing? What is the question that you need to answer? And what is the simplest way that I can get to that answer? Because a lot of times with simulation, you can take your simulation study to varying levels of fidelity depending on the problem that you're trying to solve and to the level of detail that you're trying to get it to. So understanding, am I just trying to see if this would work, or am I trying to squeeze the last few % of an efficiency out of something? Ask yourself where you're at and really boil down what the actual question is that you're trying to get an answer to. And so that starts by determining a specific goal. I want my rotor blades to sustain expected wind shear forces repetitively over a decade and understand what the strain is for that. Or I want to reduce the core loss inside of my generator. Or I want to make sure that my power electronics board can handle the thermal cycling of a North Dakota field from summer to winter for the next 30 years, and no components break off or fail prematurely. And then it's embrace the keep it simple principle. So what sort of simulation can I do to get me to that answer? Is this a feasibility study, or is this a full-blown optimization analysis? And really avoid the analysis paralysis. with how many different applications that you can leverage simulation for, it can sometimes be daunting to really narrow out what the specific thing you need to run is and get that value out without running excessive iterations that will provide, less value than others. It's important to be cognizant of that, but that's what channel partners like ourselves can also help you identify, help you peel back the layers of the onion in the problem and get to the root fundamental analysis that would be helpful for your specific application. Okay, so moving into a couple specific Ansys workflows that are relevant to wind energy. The first one we have here is a blade design. And so blade development leverages a multitude of different Ansys solutions because it is a multi-physics problem. We have air flowing over a blade that is creating lift, and that is creating rotational forces on the turbine, and that is subsequently generating energy. So aerodynamic as well as structural loading are two things that are particularly important. So for this blade design, the primary goal is to develop lightweight blades that can withstand heavy aerodynamic loads while optimizing shaft power. And so for the simulation approach, we leverage Ansys Fluent to perform blade aerodynamic simulations and iterate through various design iterations of blade geometries to identify for the same given velocity of wind, how much shaft power can be generated based off of that blade design. For understanding how aerodynamic loads will impact the structural integrity of the blades, Ansys has fluid structure interactions where we take aerodynamic forces solved in Fluent and map those to convert and solve structural forces and strains inside of Ansys Mechanical. This allows us to perform fatigue cycling and determine not only have we identified a better performing structure for the blade to generate power, but that structure also withstands the expected forces that those blades are going to see. And so the simulation outcome in this regard becomes an increased shaft power from the updated blade shape and fatigue predictions over the expected service life. So driving a higher degree of confidence into those blades that not only are they going to generate more power, but that they're also going to last in the environment that they're going to be placed into. The next one is a simulation workflow around the nacelle design. So what the nacelle is essentially it's the housing that encompasses the gearbox, the generator, and some of the power electronic circuitry inside of the wind turbine. And so design a turbine housing to maintain strength and stiffness against turbine rotational forces. So this housing is under a lot of force, rotational force from those very large turbine blades spinning. And these things are enormous. You see them driving down the road, they are very, very long. And if you get up close, they're much bigger than you imagine. So you can imagine how much force those blades spinning can create on this axle. We also think about the actual, the shear or the axial forces coming in along the housing of the mount of the turbine as well. So this housing or nacelle is subjected to many different forces and needs to be sufficiently designed so that it can withstand said forces. Ansys Mechanical is a fantastic tool to leverage here. It can utilize parametrics to perform sensitivity analysis and identify where material needs to be, where it can be removed to reduce material costs, but also maintain structural integrity and ensure that it will last without premature failure over the service life of the turbine. The outcome here is that we've reduced weight, we've reduced cost, we've maintained structural integrity, and we've also ensured that the changes that we've made to this housing are not negatively impacting the aerodynamics of the wind turbine itself. So if we make all these significant changes to improve the housing, but now all of a sudden we're impacting how the air flows through the turbine significantly, and now therefore losing power, that's moving in the opposite direction. So fluent and mechanical, again, are leveraged both in this situation to ensure that both of those criteria are being maintained. The next one is specific to the generator. So our goal here is to develop a high power density, highly efficient generator that can generate power to the grid over varying wind speeds. So if you think of a generator or a motor, when you plug it into the grid, it's going to run at the synchronous speed, 60 hertz for the United States. So if we think about we were just to place a simple AC generator onto the grid and spin it, if we're spinning it at a speed that's non-synchronous, we're going to meet resistance from the grid. Generators that are developed in wind turbines acknowledge this and understand that for their specific application, the generator is expected to spin at varying speeds because the wind is going to be changing. So they leverage what's called a doubly fed induction generator, and what that allows us to do is to utilize power conversion circuitry and convert the energy that is generated from the turbine, convert it into DC, and then convert it back to AC to connect into with the grid. This allows us to operate at speeds that are non-synchronous and adjust for variability inside of the wind. But ultimately, the design and development of that generator, it's critical that we are minimizing losses wherever we can so that the power that we've already gotten into the shaft from the wind, we're not losing any more of that than we possibly can through power conversion. So the simulation approach here starts with investigating and developing that generator inside of a tool like Ansys Maxwell or Ansys MotorCAD. Inside of this tool, we're able to look at different optimal pole and winding configurations to minimize areas where we would take a hit on efficiency. Big areas would be inside of losses inside the conductors and winding, as well as inside the core of the rotor and the stator, where magnetic energy is being lost. So minimizing those losses so that we have as much energy transferred as possible is how we can leverage simulation in this realm. But Ansys also has the ability to take this a step further, and after we've characterized our generator, we can utilize Simplorer or Twin Builder to build up a model that represents the generator and its power electronics conversion and its ultimate connection to the grid. From here, we can then try out different scenarios of varying wind speeds and get a characterization and understanding of what sort of power output we'd expect to see in those different conditions. And the outcome here is that we have a generator that's as efficient as we possibly can. It's able to work over varying wind speeds, and we have a characterization of how power is generated and its interaction with the grid over those different speeds. I don't have a specific slide on the power electronics magnetics, but that's another area that can be leveraged here inside of simulation. When we have a DC to AC or an AC to DC or an AC to AC conversion, there's oftentimes magnetics components incorporated, like transformers, and Maxwell can also be leveraged to optimize and design any transformer that you have, aside from the electric machines or generators in this specific application. And then the last simulation-specific workflow for the energy industry and wind energy that I'd like to talk about here is electronics reliability. So inside of all those power electronics, where things are being converted and switched and connected up to the grid, we have electronic circuitry. Those electronic circuitry are often placed on printed circuit boards. And just like the rest of the wind turbine, these things are hopefully going to be installed for a long period of time with minimal maintenance. So having a board last the entire lifespan or close to it for the power electronics is certainly desirable in this industry. So our goal, what can we do to ensure that our power electronics are reliable and can withstand 30 years in the field while subjected to thermal swings and vibration? Thermal swings being they're outside, they're subjected to the highs and lows of the temperature of that environment, vibration from the wind, rotational forces. We want to make sure that these boards aren't going to prematurely fail. So our simulation approach here is to leverage Ansys Sherlock to predict premature field failures on these PCBs and other power electronics systems. Sherlock is a life cycle predictability prediction tool that takes in your PCB CAD information that includes information about your bill of materials and your components, and performs FEA analysis for thermal, vibration, and shock, to name a few, to characterize and understand and predict how long this is going to last in the field. So the graph here on the right that you see with the curve pointing up and to the right, the x-axis on that graph is the life cycle in years. The y-axis on that graph is the probability of failure in percent, 100% being at the top, 0% being at the bottom. And the little box that is drawn around this graph in the lower left of it is showing the target performance for that specific product. So in that instance, for 10 years, no more than 20% field failures due to vibration is what that is currently orchestrated as. So what Sherlock is going to predict by running various vibration thermal shock studies is give you an idea of how long that specific board is going to last, and if it's not going to last, how long it's expected to last, all the way down to discretizing individual components and telling you which ones are problematic and maybe worthwhile to try changing. So that might be changing how the board is mounted. That might be moving a couple components around to avoid an area that's having a little bit of flexion indicated, or changing the component to a different package entirely. Sherlock helps you identify these things prior to the board being fabricated, installed, and physically tested. Oftentimes in industry where PCB systems are subjected to these tests, Sherlock is not always, sometimes, but not always, able to be used completely in lieu of those testing. In other words, it's likely that for your specific application, if you are doing environmental testing like shock and vibe and thermal cycling, you're going to still be doing those tests anyways as part of your design verification process. But what's unfortunate is that you get halfway through that test and find out that you're failing. Sherlock gives you that confidence prior to boards even being fabricated that you're going to be successful in those tests that you perform later on. And then just a couple closing remarks here. Energy demands are only going to increase, so developing efficient energy systems is critical to keep up with the expected demand. But engineering problems can be complex. It's very easy to get stuck in the weeds to determine what is important and what is a nice to have. And simulation is a powerful tool to help you uncover and develop whatever product you're working on. I know we've been talking about energy and particularly wind energy, but for whatever product you're currently working on, simulation is a powerful tool to help you. And the Ansys portfolio very much likely has a solution that can help you for the problems that you're facing. And we want to be, your helpful partner to identify and kind of parse through those weeds and understand what is worthwhile to simulate and help you build up something that can drive valuable, useful help. We do that through anything from helping you acquire the licensing, training you on how to be effective and useful on the tools. And if it's an area that you don't have experience or interest in driving yourselves, we also have simulation consulting that can assist you in these objectives as well.